Bonjour à toutes et à tous. Tout d'abord, un grand merci pour votre présence. Au nom de la Fondation Pavillon Cycli, nous sommes très heureux de vous accueillir pour cette troisième conférence du cycle Simplexité. Nous avons la chance de recevoir ce soir l'ingénieur, architecte et rechercheur Philippe Block. Avant qu'il nous présente son travail plus en détail, donc en anglais, comme vous le savez, je vais vous faire une petite introduction en français de son parcours. Promis, elle sera courte. Philippe Block, vous débutez vos études d'architecture et d'ingénierie structurelle à l'université de Vrije à Bruxelles. Vous poursuivez ensuite votre parcours académique au sein de la prestigieuse université MIT en obtenant votre doctorat en 2009. Vous êtes actuellement professeur d'architecture et de structure à l'École polytechnique fédérale de Zurich, où vous dirigez le Block Research Group avec le docteur von Mele depuis 2009. Vous êtes également le directeur du Pôle de recherche national suisse sur la fabrication digitale et numérique depuis 2017. Votre travail et celui de votre groupe se concentrent sur le développement de solutions durables et circulaires dans le monde de la construction. Pour cela, vous développez la conception structurale assistée par l'ordinateur et la fabrication digitale. Vous mettez également votre recherche en pratique avec la création de sociétés telles que la Startup Vault, où vous concrétisez des solutions de plancher nervuré en béton qui sont extrêmement optimisées, en minimisant du coup la matière, permettant ainsi de minimiser l'empreinte carbone. Vous recevoir aujourd'hui dans un contexte où les enjeux climatiques et de développement durable sont de plus en plus importants était une évidence pour nous. Votre travail visant à minimiser la matière et à optimiser les processus constructifs est une inspiration dans cette recherche de faire mieux avec moins. De plus, votre travail s'inscrit parfaitement dans le thème de ce cycle, à savoir simplexité, des solutions simples à des problèmes complexes. Les formes géométriques que vous développez d'apparence très complexe sont en réalité extrêmement simples, puisqu'elles permettent de transmettre les charges de la manière la plus efficacement possible, à l'image d'un arc sous son poids, au final, ou de cette coque que nous avons sous notre tête ici de 9 cm d'épaisseur, portant sur 54 mètres, son propre poids. Je vous remercie encore une nouvelle fois pour votre présence et vous souhaite une excellente soirée. Philippe, the floor is yours. Merci.
Thanks, Frédéric, for the nice introduction. Thank you all for being here. Very special indeed as a structural designer to be able to present under an important inspiration and an idol for many of us. So today, as said, everything we do is driven by, of course, the pressure that we have on climate, on resources, and so on. And I directly want to start by saying disrupting concrete construction and claiming that concrete can be sustainable. So I hope that at the end of my talk, you will agree with me that we need to approach sustainability, sustainable construction with much more nuance than many of the attitudes that governments are following and so on. It's maybe too provocative to start with, so let's dive in. Also hearing the introduction, I hope that I'm preaching to the choir that we need to take our responsibility as an industry, so buildings and construction globally, roughly it depends, you see all kinds of numbers, but this 40% is easy to remember, and that is on a global scale. So our industry is responsible for 40% of human-made greenhouse gas emissions, resource use, so virgin materials, waste production. In Switzerland, for example, it's almost 70% of the waste comes from construction demolition. That is spectacular, right? So there is a lot to be done there as well. And then energy. Just to set the frame a bit, and don't worry, I just want to first set the references here, and then I'll dive in. But there's two types of emissions, so impact of our building. The pink one is the operational one that increase throughout, so that has to do with operating the building, heating, cooling, electricity, and so on. And then on the blue is the embodied emissions. So today I will be talking about the embodied emissions as a structural designer, but also actually because with the embodied emissions we really need the new ideas. Theoretically, if there would be political will, and also the infrastructure to follow, but there is enough energy on this planet, we could actually go to almost zero on the operation. But again, we don't have such a silver bullet for embodied emissions. I will come back to this equation. I mean, it's a very simple one. It's what are you looking at? Global warming potential. So those are the emissions associated, embodied emissions in a building. So the emissions that come from the material, the construction and things like that. So again, everything until you open or use the building. So if you want to understand what your impact is of your building per year, then what really matters is MQ stands for material quantities. ECC stands for embodied carbon coefficient. So for all materials, you can calculate what is the equivalent emissions associated to them. And T could, for example, be the service life. So basically, how long are you using that building, those components, those materials at the end? So what I will be talking about is we should question what we need. So can we do with less material? We should also try to design with the best possible materials, so to go to low carbon solutions. And then this is exciting and becomes increasingly important, is not to do less bad today, but actually already thinking of the next lifespans or extend the lifespan of a building and so on. So our group approaches these topics like this. So the first one is strength through geometry. The second one, material effectiveness. And maybe notice that I use the word effectiveness and not efficiency. In the more German tradition of lightweight is good. Well, not necessarily. Remember, it's about what materials, how much of materials. So if you use very little materials, but you use, for example, carbon fiber, then you're offsetting directly what you're doing there. And then the last one, circular construction. So strength through geometry, as in the introduction mentioned, I was lucky to work with John Oxendorf at MIT, and I thought of doing high-tech stuff at this famous institution, but I ended up working on historic structures in masonry. I developed methods to understand why they stand, how they stand, and if there is something wrong, like the Notre Dame, for example, what to do. And the more I was working on these structures, the more I was entirely blown away, and I realized that modern architects and engineers might have forgotten something. And why am I saying this? These vaults here, this is at King's College at University of Cambridge. They are spanning 13 meters in this case, so 13 meters, with only 10 centimeters of simple stone, right? So no reinforcement, these are just stones. And this is still standing after more than 500 years because it has the right geometry. If you translate this 10 centimeters of over 13 meters, then that is literally as thin as an eggshell, right? And so it is not a continuous structure. These are big pieces held together. That's when I really realized, when I started my group, I switched from historic preservation to actually try to bring this knowledge back into modern day practice. So very early on, we developed these tools based on graphic statics, very graphical tools that really give insight to the designer to explore the beautiful realm of efficient compression structures. We developed tools like RhinoVault that we shared freely so that others also could jump into it. But you can do whatever you want on a computer, right? So you can visualize whatever you want. And that is why we took the 2016 Venice Biennale to make a statement. We built this, we called it the Armadillo Vault. What you're looking at is 16-meter spans, 399 pieces of cut stone that are held together because of their geometry. So there is no mortar, no glue, no reinforcement, entirely dry assembled. And we went so extreme to really make sure that no one would say, but it's the mortar that is holding it together, which is, of course, a stupid argument. But so here, this extreme statement was there not only to also celebrate the beauty of such balanced geometries that are very naturally kind of standing because of their geometry. But so here with this older project, so we finished this in 2016, I want to maybe hit one thing, is that I think this image speaks for itself, that if you get the geometry right, if you get strength through geometry, you can significantly reduce the mass needed to achieve certain spans. Again, we are in a building that shows this very nicely. A second project that I want to show as a backdrop, I was lucky to be able to do the engineering on this one. It's a project by Peter Rich Architects, John Oxendorf, Michael Ramage. It's in South Africa, literally in the middle of nowhere, Mapungubwe Interpretive Center. And there the concept was to reintroduce these, or in a very different context, to introduce this traditional vernacular technique of Catalan vaulting, where you use a lightweight tiles and a fast-setting mortar to build in stable sections, as you see, without the need of support from below. And so that was one of the reasons to introduce this system, because it allowed local resources, so local laborers, these are farmers, these are carpenters of the local village that were trained in this technique. All the timber that you see is not formwork, it's not holding the shell, it's actually to describe the shell, because we are literally using unskilled labor to make sure that we get the right geometry. Local resources, not only in labor, but also in materials. So a year in advance, all the tiles were made by taking the local soil with 7% of cement, manually pressing, and then just air drying for 1 year before using. I mean, it's a beautiful project, but why I'm sharing this with you is this image, the contrast between these two images. So on the right, you see that the women from the village are carrying the tiles in very small packages. And that is because these tiles are designed to take only 2 megapascals in compression. So if you're not an engineer, then that probably doesn't mean anything. So that is 10 to 15 times less than a standard concrete in compression. But if you take these tiles, it breaks as easily as cold dark chocolate. Of course, a superior Belgian one. No, sorry, that's... okay, but so this material, intuitively, you would never consider structural, right? And look here then on the left, when you indeed place this material where naturally the forces flow in compression, which is the beautiful arch, you see that indeed the people are already laying the other tiles, and this is still the permanent structure for this museum. So this is a second thing that I want to talk about, but let's maybe quickly, a small learning opportunity here. So an arch is very good for a certain loading case. If you don't have double curvature like here, to take all other live loads, or in the armadillo vault we had this double curvature, then you need something else to find the red line is where these compressive forces want to go to the support. If you have a live load, a user, whatever, that is not the design load, then you see that we could not find a compression line inside. That would mean collapse. So one trick you can do is to locally increase the structural depth by, for example, placing these stiffening wells. And here you see that that offers a direct path in compression for your forcing to go to the support. If you then add a tension tie, because this arch is pushing, right, on its neighbors, if you add a tension tie, for example, in steel, what we have just done in the last 30 seconds is basically we have provided something entirely performance-wise, entirely equivalent to a reinforced concrete beam or floor plate, but one that uses 70% less material, right? So this is not rocket science, literally not. This is just physics. But so that is what we are facing when we actually reintroduce these good geometries. Not only that, we not only place material exactly where needed, because we follow the forces, we also have very low stresses. So again, for the non-engineer, stresses means how strong does my material need to be. So if you have very low stresses, you can activate the weak material that I talked about earlier. And this is important because there is almost generally a one-to-one relationship between how strong a material needs to be and how much it emits. So how much, what its carbon footprint is. So that is a second opportunity that we get with getting the geometry right. By introducing strength through geometry, we get those two things at the same time. You can significantly reduce the mass, right, to 70%, but you can also activate very low strength, low impact materials. So that's a great opportunity. What drives me is the big challenge. Of course, we have challenges locally as well, but globally, we will have to provide adequate housing infrastructure for at least 2 billion more people that will be on this planet in the next 30 years. People like Bill and Melinda Gates have translated what that means for our industry, that we will be building the equivalent of 1 New York City every month for the next 40 years. That's absolutely crazy, right? This is another reality. This is not my vision of my future environment, but it's another reality that we are denser, that cities attract, that we go taller, and so on. And I want to talk a little bit about this building, these medium high-rises, let's say 20 to 40 stories. If you look at these structures, you see consistently a distribution of mass like this. So what are you looking at? The blue is the weight of the structure. So you see that actually the structure is mainly there to keep itself up, not us. Totally different than the chair that you're sitting on, right? So the chair can take much more than what it weighs. Our buildings are basically holding only themselves up. We are only a small fraction of these imposed loads that you see there. 2% of the weight in a building, these medium high rises, are us using the building. If you then zoom in a bit more, then you see that more than half of that structural mass is in the floor. And I'll share maybe already a quick intuition. Gravity comes down, columns are vertical, perfect alignment. We have decades of advanced research for the mega tall buildings, so we understand how to stabilize, brace our buildings for lateral loads really well. But then you have a very thin element, our floor slab, and I showed you that actually, naturally, the forces would want to be like an arch, and that clash causes exactly this. Indeed, this 1 New York City every month and so on also means that about 200 billion square meters, I don't know if you can imagine that, that is gigantic what we will be building in the next 30 years. And globally, we cannot say stop construction. That is not possible because it's not here that all these needs will be. So please, let's not do it like this. That's kind of what I'm saying and where we are acting. All right, so maybe let's go to a first project, this high-low project. It looks crazy, I know, and but so it achieves what I wanted to do. So it's crazy, you're curious, you go visit, and then you learn about what really matters, and I will come to what really matters later. But because the roof looks so crazy and because we're standing under a crazy shell, let's talk a little bit about the roof. So what we did in the roof was actually, can we reintroduce these beautiful shells, but without needing all the formwork and the waste during construction? And I will show you what I mean by that. So that shell, I mean, not as spectacular as this one, so I feel very humbled. I need still a long way to go. This shell is 5 centimeters, and we have only 20 meter span, so not 50 and 9, so that is nicer. But we do a 2-layer shell, so it's 5 centimeters and 3 centimeters. What we were doing with this roof is that you can have very efficient surface structures in concrete, and here I see some people already shaking like that's maybe a bit unfair, but because maybe you know where I'm going with this. This beautiful structure, and it is a beautiful structure, there was a beautiful structure before that. Perfectly detailed timber construction, really beautifully detailed. That timber construction did need a lot of scaffolding, did need an entire foundation end. And after 28 days when the concrete was hardened, then it turns into this, right? That is what we wanted to try to show with this roof. Can we go from this brute force, kind of forcing a material to stay in place, use all this single-use material, this pink that I showed there, needing the entire foundation? Can we ideally go to what we have on the right with these flexible formworks? So basically, I make a small interlude because here we will not use strength through geometry only in the shell, but in fact in the formwork. We will use the equilibrium of the formwork to build the shell. So in this case, the equilibrium is the inverse. It's a tension-only structure, super lightweight. We developed a kit of parts where we developed a node such that the node actually helps a regular worker to know exactly what to do on site. So the entire complexity is reduced by what do you need to do at the node. For example, it says where to place the reinforcement. It says how thick your element needs to be there locally. It shows you how to install the insulation and so on. So in order to do that is, again, another statement of you can do whatever you want in theory on the computer. In reality, you will have tolerances. So we pre-stress this cable net to be exactly where it needs to be. But even in Switzerland, the edge beams might be off by a few centimeters. And so you need then a strategy to not only know where your geometry is, but also to redirect. You have about 90 trillion options, which are the ones that bring your formwork exactly where it needs to be. So that is, of course, needed when it's nice with the title Simplexity. Yeah. So this seems simple, but you need to, of course, then enrich it with algorithms. This is what I said, that a worker has very local control of what he or she is doing. And then this was, the client asked us to do a full-scale prototype, mock-up. And this is then the mock-up that we have. Again, the span here in between is maybe 20 meters. In total, 180 square meters of concrete surface. This is only 3 centimeters. But then we optimized, we learned from the prototype, we went on site, and we used the same kit of parts, but reconfigured to build this shell again. So with a fabric formwork, so the cable net carries the wet concrete, and you cast on top of the fabric. So this is then how the formwork looked like. And then at the end, finally, we could then realize this shell. I'm very proud to say that this shell was probably the only thing in the entire project that was on time, on budget, and within 4 millimeters of tolerance. If you know concrete construction, 4 millimeters of tolerance is really crazy. So how could we realize that? Again, the hint is a little bit in the note. So we basically pre-designed all the different conditions, like, for example, how to finish our shell, how to integrate the beautiful facade line, and so on. That was part of the formwork so that we really could control all of these tolerances. We prototyped all of these solutions with our partners so that once we go on site, everything works indeed. So here you see that the facade elements are in there. We use the same elements in the nodes to know exactly where to place all the insulation, because here we will cast the second layer of concrete and stiffening ribs running in 2 directions. And then this is where it's standing. Another reason that we could really bring this together is because we very consistently did this in an integrated computational way with the open source platform Compass. I was very pleased when our engineering colleagues called our approach BIM on steroids. So that is what we did with Compass. We basically, every single aspect, all the different hundreds of iterations were easily kind of carried by connecting all from fabrication to the new algorithms to FE and so on, but also to coordinate with all workers, right? So instead of passing on information and having loss of information clashes, we work with a central kind of infrastructure, and we negotiate all the interfaces with all the contractors, and that made that we could do this craziness in today's context with a total innovation on the building side. All right, so strength through geometry, I hope I convinced you, particularly with the early projects, of not only the beauty, but also the importance of getting the geometry right. Let's maybe talk about material effectiveness, and let's talk about the gray elephant in the room, concrete, and why we are pushing innovation in concrete. So concrete, typically when you have a floor, so here you see the columns and this is the reinforcement, then you come in, these are very typical ways that you look at concrete. We also know that if you work in concrete, when we talk about concrete typically, we indeed talk about reinforced concrete, and that also means that the end of life or the extending of a lifetime, as you see here, is not that straightforward. We also know many people that are happy to say, in a very plakativ, to say it in German way, wood is good, concrete is bad. There's big articles that say most destructive material on planet Earth. Well, it has a big impact, but where does it really come from? Is it correct to just dismiss the material? And again, you remember the 3 levers that I talked about. It is not just about the material, it's about where, how much, why you use the material, and then the lifetime is also important. I can show you all kinds of things like that. Per unit mass, you see actually that concrete is one of the best materials. And steel is, for example, much higher, but I don't want to go into this too much. when I show you this, maybe you already have a sense where I'm going with this. I consider, not only me, but one can consider concrete as an artificial stone, meaning that this is a material that is happy in compression, not in tension, not in bending. So the natural geometries for stone architecture is then also the natural geometries for that beautiful material that we can cast. And indeed, we already looked at this, but to be more specific, instead of forcing that material to be in a geometry that it doesn't want to be, this straight line, but reintroducing the natural geometry for a compression material, this is what you get. Again, for free. If you only look at the structural properties, this is what you get. 70% less concrete, 90% less steel, right? So I'm not talking about small stuff. So it's about reintroducing these kind of new idea, these old ideas in a contemporary way. And so then we started to develop, to go beyond the simple arch with stiffeners. This is a 3D arch. You go to 3 supports, like a vault, and then you see that the stiffeners accumulate to the supports. That means that we have compression only under all loading cases in the middle, and then we just resolve it with a very simple tension tie. So coming back to the high-low project, that is what I want you to notice when you visit, not a crazy roof. I mean, the project started in 2011 when I was a very young professor. Then it was cool to do shells and so on, sustainability. Only really nerds were talking about it and so on. So now we build it. So I'm fully aware that you can be critical about what we did with the roof. There's computational innovations and so on and so on. But now I want to talk about the floor, and that one hopefully will surprise you. So in the same unit, the mezzanine level in between has 2 floors of roughly 5 by 5 meter span. But what's made me special there is that because we get the geometry right, these floors are low strength, fully unreinforced concrete, and the structural thickness is 3 centimeters, right? So for 5 meter spans. And this is a properly occupied building, so people are working in this building. There is no acoustical issues and so on, because actually the geometry helps us there, the stiffness of the geometry. Of course, I realize that this is a bubble project that we can do with a lot of funding in a very specific, it's a real project, but it's still not a big impact. So let's go back then to what we were talking about here and take one of these buildings, for example, 25 stories tall. So let's do a very boring design. We have some cores, and we consider a typical reinforced concrete building. What would happen when we now introduce the stiffened vaulted system that I shared with you? So already we know that 40% at least, for example, if you go taller in Chicago, the average is 60-65% is in the floors, right? So to give you a sense, it's really the floors is what we need to solve first. So we know that we have 40% there, but then also we can have these savings. You see that it's not 70 and 90. That is because in a building that is not just a one floor, we have fire, we have enhanced acoustical kind of requirements and so on. So you have to put a bit of material back in to get these other requirements. Again, so what we were doing, 25-story building, very simple floor plan. If you introduce these floor plates, then you save 7,500 cubic meters of concrete for this one building, which translates to more than 1,200 concrete trucks that would not have to go to this one building site. But also, per story, you save 20 kilometers of reinforcement steel, which nicely rolls out from Zurich, where I happily live and work, to Brussels, where I'm proudly from. That's a long distance. That is more than 600 kilometers of reinforcement steel that you would save on this one building. But as I made a statement in the beginning that we should not be carried away about the material, we should also not be carried away just about the volumes. What really matters is the combination, right? It's the material quantities, but it's also what materials that we use. So what are we doing when we introduce these floors? So structural geometry, remember the armadillo vault, directly gives you a cut, right? So directly gives you a cut on the quantities, that's great. You can use state-of-the-art new materials, so these low-carbon concretes, I will talk about this a bit more later, to address the material side. But also remember, by getting the right compression geometry, we can actually also reduce the strength of the materials needed. So again, when we look at the floor, strength through geometry gives us these two things at the same time. We can directly cut the mass, but we can also have lower stresses. What does that mean? In our floors, we don't use our typical C30 concrete, but we go to a C16 low-strength concrete. And just because we don't need it, the stresses are so low, and so that gives us an additional 20% cut. And then we use state-of-the-art kind of materials that are available on the market that take the clinker out of the cement. So clinker is the most polluting aspect in cement. So for example, the CEM3, CEM3A, B, calcined clay cement, things like that, right? So not the old school OPC cement, by the way. If you use that, I think that's borderline criminal. You should really, certainly in Switzerland, use greener concretes. But look how exciting this is. You have only a cut of 60% of the mass, but if you start to accumulate, you actually have 90% reduction by actually combining, by really addressing the two pillars at the same time. So the steel we keep as is. So that means that today, when we're building our projects with this floor, we have, compared to the status quo, our reinforced concrete floor plate, we have 85% reduction of global warming. Then to bring the point home, just to clarify, yes, if you would, at a big premium, get the greenest materials out there, then you could maybe reduce by 50%, right? The material itself, concrete, 2/3 you can cut, but there's still the same amount of steel in it, so that offsets your equations. So, but the volume, the amount of materials is the same. What we do is we do these two things at the same time. We have a bigger cut, even though 50% would already be nice, but we have a much lighter element. What I'm showing here, by the way, is that if we were to use the old school OPC, so CEM1 concrete, so that doesn't have any clinker replacement, then still we would have an 80% cut on the global warming, just to show how important design is versus actually the choice of material. But now what's cool for us is in how we go forward with these projects is actually this. Because what does this mean? We have an element that is lighter. In fact, we're as light as a timber construction, because what is the real limit? It's always acoustics. It's always kind of contact noise. Oh, this is very solid, yes. And then noise traveling through and so on. So that is our limit. So we are lighter. We save on the columns. We save on the foundation. So that means that if your building is tall enough, then you can give all of this sustainability to your client at the same cost throughout. And I think that is an important opportunity, because most sustainable solutions have what is called a green premium. It means that sustainable means more expensive. And so you need to start to look at it holistically to also have a business case, right? Because otherwise I have a nice story, and then so what? Because at the end of the day, it's really money that will matter as much as the intentions are right. All right. Then now to go to circular construction. So first I want to do a small side tour again, and I will land with our floors at the end. For this, I want to show a project we did with Zurich Architects in the context of the Venice Biennale. This is already now 3 years ago. What you're looking at is a concrete 3D printed, fully unreinforced bridge. Bridge, okay, you can also criticize that there's nothing to bridge, yeah, there's no water, but it's a real bridging structure, and it's entirely unreinforced. How does that work again? I already made that connection between concrete and it being an artificial stone. So if you then use these kind of stone techniques, like a global discretization, to make cuts that are as orthogonal to the global force flow as possible, a local alignment of every single layer follows the same logic. That is exactly what we did in this bridge. So we combined a top-level global discretization, like a Roman arch, for example, and then we used non-parallel 3D printing to exactly place the material where it wants to be, to also on the local level to be perfectly aligned with the force flow. So then you can really take advantage of opportunities of 3D printing. So here on the left, you see we place material only where needed. We want a structural depth but we don't want it solid as a massive piece, so we hollow it out in the middle, and on the right we place material exactly where needed, again, along the force flow. So this is one of these bifurcating elements, for example. But then what is quite remarkable is that the bridge is in diagonal 21 meters, so the main span was 16 meters. This bridge was built in 53 independent elements, and all of these elements, all together, it took 84 hours to print all of them, right? So that is then also exciting, that if you have this integrated approach where you not only start from a structural logic, but you fully understand the fabrication constraints, then you can also change the how fast you deliver a project. We then assembled it in a very traditional way, dry assembled. So half of these people are long-term collaborators from Burgen Creations, and half of them is actually our research group at work. And so here you see we really, again, dry assembled it. We used these neoprene pads in between to have something equivalent to the lead sheets that you have in traditional granite construction, for example, so that local stress concentrations don't cause cracks, for example. But what I was excited to do with this project was not just to celebrate again like another pavilion with Zaha, okay, cool. It looked cool, I think, personally, but what we really managed is to emphasize multiple opportunities when you look at concrete as a masonry system. You reduce, I showed you that we place material only where it really wants to be. We have actually quite a robust repair strategy. For infrastructure, this is relevant, right? That you separate materials, you see all the components, you can take them apart and so on. You could potentially reuse it, because as easily as the elements come together, as easily you can take them apart and move somewhere else. Maybe not relevant for a bridge, but perhaps relevant for a floor. So I will come back to this later. And then last also, rather than having the messy demolition site that I showed you with all the rebars and so on before, here we have a very clean deconstruction and an easy recycling. So that is then, the project was there for a couple of months, as always for the Biennale. You see also some features that have something to do with how it was made. Rather than considering them as an accident or something to fight, we celebrate them and we express them as kind of an additional feature also below. We really wanted to make this piece very legible and exciting to look at. But again, here you see masonry on two levels, right? And by the way, what I liked when visiting this project, there were actually 54 blocks, because the contractor didn't listen to what we said, how they had to install the bridge, and just picked up one of these elements, and it broke in bending, right? And so actually this element here, that's the 54th block. You just put it together, and it's, again, the nice structure. So this was also a nice demonstration of really these opportunities of very pure circular construction opportunities when you consider concrete as an artificial stone and a system. All right, so we achieved quite a few things in this project. One thing was not there, the ink. The concrete ink was very polluting, right? And so we had a chance to do a second project, Striatus 2, which we call Phoenix. And Phoenix because it emerged from the ashes of Striatus. So we shredded Striatus and we 3D printed a new bridge, this time a permanent one. It's a permanent bridge in France. I don't know if you've worked in France. A lot of bureaucracy, so I'm very proud we built a real project with so much extreme innovation in France. And it's 100% recycled material in this concrete. And it comes mainly from Striatus. So also what we did is that we optimized how to install this. Several pieces could be installed with these standard elements, then they're lifted in place. And so here we go then, we didn't design the foundations, you see there a lot of waste in the foundation. I guess our business is about compromises, no? So here it's being installed. Also interesting, we did the calculation of the embodied emissions. And we used, again, this neoprene because it's a very kind of forgiving material to assemble such an extreme masonry system. And the neoprene pads, right, that seems like not a lot of material, is the same embodied emissions as the entire bridge. So that was a good lesson. Next time we will have to find another interface kind of material. So it's in Lyon at the Innovation Center of Holcim, but It is a permanent construction. All right, let's go back to high-low because I talked already about the floors. I hope you can appreciate that we had 3 centimeters, unreinforced, low-strength concrete. I think I was pushing the boundaries already enough in a modern-day context. So we built it with a one-off, super wasteful formwork, right? We also had the counter mold was left in place. So we only achieved to demonstrate basically the efficiency part, but not the real circularity, not the real efficiency, also when it comes to shaping these structures. So let's go back to our equation here. What we already looked at is the top. So now let's see how circular construction can really extend the service life of our structure. And for this, I want to close here now then with the Ribbon floor system that we have developed and that we are now commercializing. So here really everything is coming together. So as all the projects, we use low strength, low carbon concrete. We do an extremely disciplined separation of materials so that we never jeopardize the opportunity of an easy, realistic and clean recycling opportunity. It is fully unreinforced. That is not unimportant. We don't have embedded reinforcement that can corrode, that can cause all kind of stress, incompatibilities and so on, that over time cause issues. So we only place material in compression where needed, in tension where needed. We now introduce prefab, right, so that we can be more precise and also fast in the installation. Again, this is also done because we need to fight this green premium. If we can deliver our projects faster, then we can also again give value to clients and give them no excuse not to go for a sustainable solution. And then last but not least, I already mentioned this, it's literally dry assembled, so you can take your elements apart and you can use it in other projects, right? So we have all these circularity options. Of course, we have to do, these are the KBOB data that we use, because that's the reference here in Switzerland. So you see where we are there on the left. If you really follow what I say here, if you implement this in your projects, then you do much better than any other floor system out there. And I just say this not because I'm proud of this or I want to sell you my floors, although yes, let's build a lot of these together. But it's just to show that if you do something consistent and listen to what the material really wants to do, this is the benefit you get, right? So not like small kind of peanuts things. It also could look nice. This is an early prototype done by Matthias. And so because of all this interest and opportunity that was created around high-low, we had to set up a company. It's an ETH spin-off. It's called Vaulted, because that's what we do. We do vaulted floors. And we have, I'm happy to report that we have a lot of projects underway, also with really big clients. But the one that actually 2 days ago, so this is the first time I can officially say this in a lecture, the project that we won with Gigon Gouillard in Zug, yesterday went in Bouwproject. So everything about the floor is accepted. So all the tests that we've done have been accepted. And we go on the construction site in June. As you can see, the entire building was actually designed around also the aesthetical opportunity of introducing these floors. Took us a lot of effort to get there. 3 months after the competition, we built this. This is a one-to-one, not prototype. This is a mock-up. So we did a full test. So vaulted, designed, engineered, fabricated, and then developed the entire system, how to install it. And only the contractor does the lifting of the crane. Everything else was provided on site. So here you see again dry assembled. In this case, we use a reversible mortar to fill the gaps so that we don't have acoustical leaks, we don't have issues with fire, but it's fully reversible, so when you take it off, it would just crack off. There is no bonding at that interface. Another input to give is that this panel, so this is 6.5 by 6.5. We have another project in Brussels that is 10 meter span, so that is the range that we are talking about. Really efficient, between 6.5 and 10, even maybe 12 meters could be possible. We install one bay like that in less than 2 hours, right? So that is what I mean about the prefab, the fast delivery, the full integrated project delivery. So here's some images of the process. This is my right-hand man, Tom. He's also from Belgium, so we do everything together. And how exciting is that I can do all of this with my best friend. I know him much longer than both of us know our wives. So it's a special marriage that we have, the two of us as well. But so here's again clicking it in place, and then this is where it is. Unfinished, it looked like this from the bottom. The client really was, I mean, you can imagine that doing this, but I forgot to say that the project has 7,000 square meters of RFS floors, so we will be building 180 of these elements. 185 pieces that need to come together 2 hours at a time, so that's going to be exciting. But the client was not directly convinced, right? They loved the story, they were happy about the numbers and so on, but we had to do very extreme load test here, nice ghetto, old school style with water basins. Easiest way to do load test, so we went up, this is 500 kilograms per square meter, for example. We did a lot of fire tests, a lot of expertise. We were tested by 5 different engineering offices that were testing the fire regulations, all the things. In fact, we can use the Eurocode. We don't need any special measure to do, but people still are a little bit uncomfortable because we're using C16 concrete, we are using fully unreinforced, and there is actually no fire code for these kind of things, not structural. Then everyone is worried about acoustics, right? Drittschall and so on. And that is nice that in the prototype we could really balance, we could really calibrate the acoustical needs by playing with a little bit more ballast there and so on, and really strategically. And we did also 8 different campaigns for acoustical tests. So we didn't get this for free, believe me, this was tough. But then this is then this mock-up with acoustical, not for transfer acoustics, but for room acoustical kind of properties. This was a design choice by Gigongoya. You can do this very differently as well with texture, like here with other materials that scatter and so on. And you need a strategy because actually a dome is a horrible shape for room acoustics because you have this focus and there's crazy echo, right? So, but it looks nice and we're very excited. It's really the first time that I can say that this is going to happen. So that is very nice. And I hope that with this, the ball will roll and that the other close to 10 projects that we're working on will also now go to the next step. So that would be nice. Not in conference for free as well. I didn't talk much about computation, but you cannot just expect all of the partners around you to deal with this complex geometry, to just take it. So we have to develop advanced tools like this, for example, is a translator between our computational framework and it's an IFC writer so that you can embed it in any project. Any architect can directly plug it in. Any engineer can directly have their engineering models and so on. There's a lot of this in the background as well, right? That make all of this possible. If you're thinking as an architect, but these things are much deeper, right? So how does that work? Well, we actually integrate all the building systems in the same package. And for example, for the World Trade Center 4 tower that we are doing in Brussels with 51N4E, we actually gave the client 2 more floors because we optimized the height, in fact, by integrating the building systems in the depth. It's now 45, so I'll say one more statement, is that I'm fully aware that we are very kind of fortunate here in Switzerland, not only that the building codes and the regulations allow us to be a bit more flexible than in, let's say, France or Germany with the Eurocode framework and so on, so that is amazing. We're also fortunate that actually people are willing to kind of put money towards innovation in order to really make a difference, so that is also amazing. And I quickly want to acknowledge that actually this doubling of the building stock, right? So this one New York City and so on, it's not going to happen where we live. And so I also want to just do a small last escapade to South Africa, where we're working with the government of environmental affairs. They have found a way to use all these non-indigenous plants that actually are polluting or are killing all the local plants. They're using this shredded wood as replacements for aggregates in concrete. And so they actually created a bioconcrete that is fully certified, that is fireproof, shot-proof, they did all kinds of tests. But they never dare to really use this structurally. So they use this for infill walls and so on. And what I want to address is, this is a picture I took myself in Addis Ababa in Ethiopia, where you see that actually they're trying to mimic how we build because they want the same constructions, but I don't have to say too much to this image. So in a context like South Africa, we want to try to make it cheaper and sustainable at the same time, and that means being even more pure. So even more pure to the Gothic cathedrals, and not a tension tie, but then we use buttresses. And so we are developing systems where we introduce these unreinforced buttresses so that you can get away from the tension tie as well, so that you can push it to that level. So we did some prototypes where we place only the high strength material where needed and then fill the rest with a low strength stabilized kind of fill to really have a very redundant kind of package. And this is again 10 times the ULS that is being loaded there on the right. Totally happy, totally unreinforced, super low strength, super sustainable material. Same idea, very different context. Here we want to activate the local labor, not do everything prefab, and so that also works. So in closing, if you look at this image, you realize that 40% of the weight is in the floors. That is why I so passionately am trying to fight all the skeptics and get there. And so we are getting there this week. It's happening. We share everything that we do in Compass. So we believe in open source. We believe in learning from each other because we are all doing the same problems in our small bubble, and we are not going to progress if we keep doing that. So in closing, I talked about structural geometry to reduce mass. The right geometry, funicular form, means vaulted arches for the compression material that I've been talking about today to reduce the carbon footprint because we can activate low strength, low impact materials. I talked a little bit about opportunities in digital fabrication, how to reduce the waste associated to non-standard structural geometry. I talked quite a bit about the opportunity of discrete masonry to have circularity in this beautiful material, concrete. And then I only gave you a hint on that all of this only can happen when we find also a more integrated way to design, and not your typical architect sketch and then engineer try not to kill anyone and a builder tries to build it as cheap as possible. That's no longer going to work. We need to find ways to integrate innovation in regular projects. And then this is my last slide. You might wonder, Rippmann, that is named after our colleague Matthias Rippmann in the middle, who passed away in 2019. He was working on this project. And so in his honor, for his legacy, we called this floor system the Rippmann floor system. And I hope we will make him proud. But that was it. Thanks everyone again for coming. Okay, yeah, sorry, 4 minutes. 4 minutes over time. Yeah.
Thank you so much for this amazing presentation. So now we can start with the question. Est-ce qu'il y a des questions? Oui.
Seismic. The first question is going to be seismic.
Thank you for the presentation. I wanted to ask about the noise transmission, the contact noise. Yeah. Do you feel this precast slab in some way?
No. Actually what happens is that it depends on the span, by the way. But what happens is that the amount of material that you need to add for fire resistance actually gets you in the zone where it's an automatic check for acoustics. A postdoc of mine has shown that through the stiffness of the shell, you can also absorb some of the acoustics. We are not using this benefit yet because we have to do more tests on this. And so basically what I'm saying is that if you saw that 70% reduction would be fine for the structure. If you reintroduce material, then actually you land somewhere. So 1/3 of a typical reinforced concrete floor plate for 8-meter spans, that would be about 750 kilograms per square meter, roughly. And so we are between 250 and 300 somewhere. That's where we land. And then acoustics is very close. And then you can, indeed, with very strategic methods like local dampeners or this layer that you put. So then these measures actually give you those last decibels, and then it's a done deal. Yeah. So it ends up being not a problem because of fire. But of course, in the long run, I want to get away from that and maybe resist fire, not with the structure, and find a way to separate that as well. And why we haven't done that, it's not your question, but I'm misusing your question to talk about this a bit. Why we have not done that is actually because of finances. We need to be able to compete with the regular concrete floor plates. Of course, we cannot compete element if you just swap the element, but I explained on the level of a building we can compete because we have so much savings on the foundations. And how is that related to your question is that multi-material casting and prefabrication and so on would add so much complexity that we haven't figured it out yet to make that financially feasible. And that is why our floor plates are a mono-material solution. So that because the prefab really needs to be updated. I'm a bit mysterious about the prefab, and that is because that's our business case. I cannot show you how we do it, but it's pretty awesome. Yeah.
First, congratulations with your very well articulated presentation, because I'm not an architect, neither an engineer, and I understood everything. So, starting with one of the words you used in the first slide, disrupting. So my question is and you say we're lucky here in Switzerland with the regulation and so on, but I think there's still a long way to go. So absolutely. How we can disrupt the norm in construction and engineering? So what is needed to do more? And the second question is more around resiliency. I understand here in Geneva, most of the construction are not really anti-systemic in terms of norms. And I don't know what I'm talking about because I'm not an engineer. So what about this aspect in your innovations?
Yeah. So the first thing, I mean, actually, it's interesting. Maybe I should not use disrupt because disrupt is never going to work, I think. You have seen this before. Clever people from the tech industry, like Catera and so on, that want to revolutionize everything. That does not work. So it needs to happen with the industry together and so on. What I meant with disrupting is more actually. It's not enough to shave off and to do kind of small things. We need big leaps. We need to really go towards zero, and that's what I meant with disrupting. Just to place it a little bit. Okay, yeah. To your second point about seismic, yes, of course, we have to design for these seismic conditions. What I presented here, by the way, you cannot build like this in Chile, in Turkey, in the west coast of the US, but you can build like this in about 85% of the world. What I always find interesting is actually. I'll give another example to answer your question. So, for example, people, when they look at these geometries, they say, but where is your diaphragm to basically bring the loads from the facade to the core? Typically, what does provide this load path is the continuous floor that we have. So it's basically either the shop or the structure itself and so on. We don't have this. And then people say, like, that's never going to work. And I then challenge them by saying, but what is actually diaphragm action? It is not that you have a continuous layer. It means that you need to provide a load path from the facade to the core. And there's many other ways to find these load paths. And so to your question as well, the floors are very stable by themselves. We see this, the Candela shells are all standing, while many buildings collapse in the terrible earthquakes that they had in the 80s. So good geometry works for all these extreme loading cases as well. But we work with the engineers of the building to actually take the seismic action in the frame, for example. If they're not happy with this, then we can reintroduce material again in the floors. But so then you would save again some limits. So I answered your question maybe in a weird way. What I wanted to bring as a message is that every single time when people are critics or skeptics, then I ask them what exactly it means that we achieve, to achieve, right? So also with seismic, you can take it in many different ways. Of course, we also need to, for these tall buildings, we have to show what is called progressive collapse, to your question of resiliency. So we have to show what happens when you take a column out. How do the forces go? So all of that is also happening in the background, but Yeah, so complexité is actually a good term because it looks simple, but there's a lot of research in the background to make this happen.
Est-ce qu'il y a encore des questions?
Maybe you could develop a little bit the design aspect of your projects. You mentioned, you said something about how important design was, and I would like maybe to hear you talk a little bit more about your collaboration with architects. Yeah. How does it work? How does shape takes place, and how do you go further with your projects?
Yes. I mean, I have a bit of a mixed kind of answer that I will give there. I also studied architecture. My team is half architects, half engineers. No, 1/3 architects, engineers, computer scientists. So that's how we work. I would like to see also alternative models where whatever your brand is, are you an architect and so on, that actually the team actually co-designs really. I think that is something that is also implicit in what I'm saying, because what I'm showing is architecture that starts from a constraint of a grid, for example, that starts from a building system. But as you see with Jigonkuya, and maybe I should have put some other images of what other architects see as an opportunity in these kind of geometries. I'm excited to work with architects that actually start from constraints. So for example, also with Saadit Architects, the reason that we collaborate is because Shaje, the head of their computational design group, did his PhD with us. And so he actually starts from discovering the geometries that come from understanding the fabrication process, for example, 3D printing. The geometries that emerge from designing only within compression kind of logics and so on. And I actually never am explicit, or almost never explicit about the aesthetics of what we do. But I do believe, and we see it here, and I don't want to compare myself necessarily to Isler, but there's something to be said about the natural. You feel that the shape makes sense, that it's natural, and so on. And that is my attitude towards kind of architecture. My experience is, though, that in architecture there's often many kind of criteria that are not defined, that are really aesthetical or opinion-wise and so on. And extremely quickly you get the benefits. The numbers that I show very quickly go down when you don't go for the pure system, right? And so I think that is a shift that we will have to make. It's not allowed to not do the best we can I don't like that line there, right? And I'm saying it a bit like that, but that's my reality in my life. And so I think that is something that we want to address, but we all need to do it together. So compromises from both ways, no? Yeah. So I'm trying not to be defensive. I mean, if in my ideal world, I do it all myself, right? But that is not going to help anyone, and that is not the model that we should. And that is also why, for example, I'm looking forward to a project where you don't even see the geometry, where it's entirely hidden, but you still have all the efficiencies, but then the aesthetic is not coupled to it. So I also find it dangerous to then imposing a style with the type of approaches that you do. And so I also don't want to be labeled like that or push for an architecture like that. But yeah.
We can have one more question.
Thank you. My question goes more towards the global outlook that you did, and I think that was really effective for showing the importance of your work, not only the aesthetic and the numbers and the savings, but also the real urgent need for these type of solutions. So I'd be curious to know, what do you perceive are the main roadblocks for introducing that on the larger scale, both in a developed world context like here in Switzerland, but then also in the main markets where these buildings are going to be built?
There is an extreme eagerness in, for example, we get a lot of requests from the African continent, where they're really embracing these kind of, because they come from a real need, from real constraints. There it's not just a financial or a kind of, I have ESG requirements with my company, and so that's why I do it. It's really because actually sustainability is coupled also with a financial opportunity, right? And so, yeah, what is needed? In our context, for sure, I mean, again, the Swiss regulator and norms is better than the EU in the sense that, for example, here, an engineer can sign off on something, right? And so can just say, we are going to do it like that without a prüfingenieur and so on that checks your work. And so there is a more direct way to do things. Here, all these tests, by the way, I didn't comment on this, but this was not, in fact, not a requirement of the client. Well, at the end, the client asked it because they could not insure the building. It was the insurance that asked all these tests, not the engineer, not the architect, not the client even. So all this investment, which ends up being, by the way, 1/3 of the total cost of the real structure, is in all the pre-work, right? And so great that the client did that, but it's because, yeah, who takes the risk? Who kind of goes to... And in that sense, I'm happy that I can tell you a story where it looks like I'm crazy or really like, what is he doing? And unreinforced and so thin that luckily I have history with me, right? That all these structures with these good geometries are still standing because they have these robust, resilient forms that activate humble kind of materials. So that helps us a little bit, but there's so much skepticism. It's really unbelievable. No, unbelievable. Actually, it's not unbelievable, it's totally believable. Because if you are investing in that and someone comes with a new idea, I mean, I'm also not sure if I would have hundreds of millions, if I would put my trust in a new idea, a new innovation that is so different than the status quo, right? There's other challenges. Construction companies have quite small margins, so there's no incentive to try something new because you might go bust. Even in Zug, for example, I was entirely shocked to find out because they gave us numbers to compare the cost of our floors versus regular cost. And then we got these numbers and then we started to calculate and we had to ask them, but how is this possible? The cost that you give per square meter of your structure is less than the cost of the materials. How is that possible? And then the contractor says, that's like that in Zug. There is so many contractors that we have to build the construction at a loss to make money in the rest of the... so that is also, I mean, our industry shot itself in the foot. Lawyers did a much better job. They all agreed we're going to charge you 400 Swiss francs per hour. That's just how it is. So our industry did not do that. But yeah, that means that we're being squeezed down. And in such a climate, no chance to come with new ideas, right? There's a lot of will needed and a lot of trust also to get there. So. Yeah, but on the other hand, this will, this trust, this opportunity is in the developed context. That's why we work in South Africa. It's complicated to work, and we don't send our solutions there. You have to co-develop it locally. We work in India, also with a large developer for lowest cost housing. Same ideas, very different version, because India is different than Africa, is very different than Switzerland, obviously, and so on. And yeah, I'm hopeful. I mean, yeah, after 15 years, I'm not yet giving up, but it has not been easy. But I think more need to be crazy cowboys like Tom and me, and hopefully we'll get there then. Yeah. But thanks for that question.
Thank you so much. Thank you.